get my timer right here, so give me a second. So I'm going to talk to you about metasurfaces and AI/ML and how that integrates into what we do at the AIM Lab. I tried to cut out as much science as possible, which, you know, as someone who does research, that hurts a lot, but and try to focus on the AI/ML, but unfortunately, you cut too much, it's gibberish, so you'll have to see how the sausage gets made, so to speak. So, well, without further ado, let's begin. So that's the title. Everyone, you can read it on the sheets, it's a mouthful, so I'll just cut in there and get straight to the point of the motivation here. So what we do is work with materials called flat optics, and it's kind of the next stage, the evolution of a process that's been going on for a couple thousand years. And so in the beginning, all optics were more or less flat optics, if you exclude the eyes, of course, where you would have some material like bronze and you would kind of polish it to a sheen and use it to direct light in a certain direction. And so back in the day, this technology's main application was in temples and in lighthouses, which is where I want to kind of focus on. So what you have is this kind of material where you'd have a lighthouse with a burning flame, and you just put the flat polished surface and you direct the light out to sea so that sailors coming into shore can see rocks and other kind of hazards in order to avoid them. And so eventually people realized that, okay, instead of just a flat surface, if we use like a polished bowl, we can steer that light in a certain direction, and so more of that fire gets sent out to sea and saves more sailors' lives, of course. And then, of course, people got even smarter than that, and they realized, oh, well, I don't want a circular bowl. Maybe I actually use this, what they call a paraboloid. Sorry, it's a mouthful too. And that actually works better than the spherical bowl. And so you can see, like, with an evolution in the architecture of the material, you can actually improve the performance of the device. So this all works well and good for the light going in the backward direction, right? But you're kind of losing all that optical energy going in the forward direction. That just spreads out. And so that's where kind of lenses come in, and this will be the intro to meta lenses. So obviously, before the industrial age, it's really, really difficult to get a hold of good glass, good optical material to kind of fabricate these things. So what happened around the industrial age, the 1800s, is Napoleon Bonaparte created a commission, basically. I like to joke it's the first small business, Sibber, so to speak, where he commissioned a man by the name of Augustine Dufresnel. He made a proposal on how he can improve the performance of lighthouses by incorporating this device called what we now know today as a Fresnel lens. And so what he thought of is, okay, you know the traditional lens that has a certain curvature to it. Actually, you don't need all that material to make these things work. You can actually cut out little chunks of it and still have the device work exactly the same. Basically economize the glass you have access to. And so that technology actually revolutionized lighthouses, and it's actually saved thousands, well, probably millions of sailors' lives, because basically it allows you to take this material and apply it to lighthouses all across the world. And in fact, you kind of saw a process where a prestige of a town was kind of demonstrated by having these kind of ornate lighthouse technologies in their systems. And so they became very popular. Not so much today, because of course we've got, you know, satellite technology, GPS. But it's kind of, this is the evolution of the meta surface technology. So metasurfaces kind of carries on that tradition by saying, okay, well, do we need to vary the height of the material? Maybe we can use the structure of the surface to kind of imitate that effect. And that's actually what we are doing with metasurfaces. So there are several advantages and disadvantages to the technology, but the main one is it, of course, is lightweight. has high resolution, and that's important for imaging, and I'll talk more about that later. You can control optical dispersion. I'll talk more about what that is, but essentially different colors behave differently, and you want to control for that, and it's harder with traditional lenses. Then lastly, tunable transmission. So if you have, lenses like I do, you usually have to have like an anti-reflection coating on them to kind of protect, make them better, get more light to your eye. That costs money, of course. So with this technology, you can actually engineer that directly into them, and that's a nice feature of them. Actually, that's the main one of the main features of them. And then, of course, there's this other part that I'm not going to talk about, where you can manipulate the polarization. And of course, the biggest attraction is they're mass producible. So once you get through the R&D process of fabricating these things, you can kind of take advantage of a process called imprint lithography, where you can kind of stamp these things out. With traditional lenses like those in your glasses, you of course have to get a slab of glass, cut it up, polish it, give it the right curvature, and then to your prescription, and then after they've done all that and charged you $1,000 for a piece of plastic on your face, then you can have nice glasses. Well, with the imprint lithography, you can kind of create those bespoke solutions and then kind of stamp them out quickly at low cost. So that's the real driver of these things. So you can kind of see them be in applications like laptop cameras and your cell phone cameras. That's the main draw of these things. But of course, with any technology, there are disadvantages. The main one being that it takes a lot of work to kind of get these things going in terms of design. So it's computationally expensive. You have to, not only with the computers, but with the individual, you take 8 years of grad school, and eventually you'll figure out how to get these things working. You need highly specialized equipment to make them, and then there's a high upfront cost in terms of time and money. But besides that, once you get past the basic R&D, right, then you can get these things going. But again, you can reduce the cost significantly from the thousands of dollars from making a solution to basically a few cents once you start cranking these things out. So that's a kind of traditional cost of R&D. So what problem are we really solving? This is just kind of an illustration of the basic effect that we're addressing. And this is the dispersion I was talking about, where the ideal lens kind of focuses all colors of light in the same direction. And I apologize to neglecting this side. It's where you basically have white light coming in, and you want the red, green, and blue light to focus at the same point. But in the same way that an optical prism bends different colors in different directions, a lens will do the same thing. And so what you really end up with is that different colors will focus at different points, and you don't want that. And so if you have light coming in at different angles, that problem becomes even more dramatic. That's the problem we're trying to solve for. And so you get these kind of optical aberration effects that we call them in optics, but I repeat myself, where you kind of have different colors behaving differently even though you don't want them to. So people eventually figured out that, okay, different materials will bend the different colors into certain directions. So if I just mix up the materials in this technology called a doublet, essentially I can kind of compensate for that. And so you can kind of see the cameraman circling our distinguished body. If you took their multi-$1,000 lens and you sliced it open, I don't suggest it, but if you did that, you would see this kind of big chunky device where you can usually tell where the doublets are by where the color separation are different kind of colors. You see the different hazes there, here, here, and here. That's where the doublets exist. And so in traditional, it sounds nice if you could do it with one lens, but in reality, you need this large train of devices in order to even hope to do the optical and aberration correction. So sorry, that's why your lenses are expensive. So with meta lenses, of course, you can reduce that down to a singular device, and this is an example of some of the work that's been done already, where they basically created a meta lens that focuses all the colors at the same point. There are a few issues with the transmission. They didn't fully optimize that, so that's why you get that coloration there. It's not chromatic aberration that I was talking about. It's just different colors have different absorptions with this material. But it kind of illustrates the point where our meta lenses can kind of solve for these kind of problems with dispersion and different focal points. So I'll quickly walk through the process of how we kind of traditionally design these things, and I'll turn back to you guys. I don't want to neglect you. So like I said before, usually you'll change the height of these materials, but instead what we're going to do is change the patterning on the surface. So what we have is these little cylinders that are proportional to the wavelength of light you're operating with. So when I say wavelength, I mean color. So blue, green, red, those are the visible wavelengths. And in order to do that with these materials, you actually have to work at the nanoscale. And so that's part of why it's so expensive to design these things computationally as well as physically fabricating them. But what we do is we'll take some material like amorphous silica and we'll pattern it. We'll do a simulation and say, okay, I want to have this property called phase. Don't focus too much on it, except you want the value to be from 0 to 2 pi, this orange line, and then you want the transmission to be roughly flat, or at least as high as possible. So in this scenario, there are little dips, but essentially you want this to be close to 1 as possible because you're going to use them in your optical device. So when that's 0, that means you can't see anything. What good is that for an optical device? So that's kind of what we're doing in terms of fabrication. So this is kind of a shameless plug, but once you kind of create a library of shapes that you want to create on your surface, you use an algorithm to kind of design the optical surface and say if you want it to be a lens, you can design it to do that. But if you want it to be a hologram, which is another area I work in, that's where you kind of invoke this algorithm to design that. So this is a paper I wrote a couple of years ago of using basically metasurfaces and flat optics used for optical neural networks, but essentially the optical equivalent of an artificial neural network. So this algorithm lets you do that, and so you can use it to kind of design these metasurfaces for various purposes. So again, end of shameless plug. So we have our partners at MIT Lincoln Labs that does the fabrication for us, and so once we get our metasurface pattern ready to go, we can then send it to them. And then you get the hologram that you're going to see out there. So that's how we normally do the fabrication. But unfortunately, the issue is that gets you a basic solution, but usually that's not going to get you the full result. So in order to kind of properly design a metasurface that has a lot of flexibility, you have to kind of use different shapes beyond the basic cylinder that I showed you earlier. And so that's kind of where we are working with, or where we're going with our research. So these are some examples of stuff we kind of examine. And so the nice thing about having this expanded metasurfaces instead of just the cylinders is you can do better control of the dispersion. You can have more elaborate holograms or more elaborate lenses and do different things as well. So in other words, we can improve the library that we're using. But unfortunately, having this wide degree of freedom comes at a cost in that it's a lot harder to figure out how to design our metasurfaces. And so that's where the AI ML comes in. So what Maisie does is it takes the data from anywhere really, but I'll talk specifically about the optics, where essentially we have our data set, our optical simulations, and we feed it into our Mazy algorithm through key value pairs, basically dictionaries. And then we have inputs and outputs, and our Mazy system basically figures out the mapping between these two, and then we can use it to make predictions in order to, in our case, the metasurface design. So it works on a simple autoencoder architecture. So just a quick explanation. Usually with a data set, if you're trying to figure out, okay, what are the key variables, what an autoencoder can do is say, okay, if this spiral has 300 data points, the 100 XYZ data, do you really need all of that data to model this thing? And the answer, of course, is no, and I know that because I drew these things and I use this basic equation. So what you really need is only 100 points, the X data, and these three variables, A, B, C, and that is basically a dimensionality, what they call dimensionality reduction. So you have 300 data points, but you only really need 100 plus 3. And that's what we want. But usually with these autoencoders, you send it the data in, you tell it to figure out this encoding space, and then you reproduce the data at the output just to make sure you really figured it out, the encoding. Usually this code space is gibberish. You can't understand it. And so what we want to do, of course, is send in a design and ask it, okay, what's that A, B, and C that we want to get that spiral pattern? And so with that, you usually require an additional neural network to get that information out. All right. So what we've developed with our partners at AFRL is this algorithm called, or this approach called a pseudo autoencoder. And so the nice thing about it is it's an elegant solution to that problem because it allows you to impose certain forms on your neural network. So I'll spin back over here. So essentially, if we're asking the neural network to figure out what's the best meta-atom, we want it to tell us the shape, for example, the material we're working with, the thicknesses, the heights, the dimensions, all of that information we want at our code space, and we want it in that form so that we can understand what it means instead of having to have an additional neural network that does the translation for us. So when we train it in this architecture, it imposes the forms that we're interested in, and then we can just run it like a traditional autoencoder. And so the nice thing is, that you get at the end is a system that can predict what meta-atom shapes we want in order to get, or you send in a certain input and it predicts what meta-atom will give you, is likely to give you that input. And then on top of that, you have a way of gauging the quality of that prediction. The neural network will take that input or the shape and then predict, okay, what's the output that is going to give you, and then you can do a comparison between that in order to see how sure it is that the shape is good. So we have a way of a metric, so to speak. And so Mazy has been designed for our optical simulations, but in reality, it's not limited to that. We have all kinds of pieces of data that goes into this algorithm. We just store all of that in a key value pair, and then we have the outputs that we're looking for. And again, we store all of that in a key value pair, and then we feed it into our neural network algorithm. So what we're trying to do is kind of the hardest thing of optics, which is inverse design. And so what we're trying to do is replace this electromagnetic simulation algorithm with our autoencoder and do kind of the modeling for that for us. So it takes a lot of the work and effort from the engineer and quickly allows us to kind of develop the technology that you would have difficulty in normal circumstances. So kind of quickly go through this. The backbone of our architecture, of course, is Python Python, and I actually grew up writing code with TensorFlow, so I stuck with it this whole time. I can use PyTorch, but I just use TensorFlow, and our architectures based on that as well. Our other architectures are based on that as well. Our CWA code, our electromagnetic simulation is based on it. And the nice thing about it, of course, is that it takes care of a lot of the simulations or the materials, or sorry, excuse me, it takes care of the interfacing with the CPUs, GPUs, and we don't have TPUs, but it can take care of that as well. So that's kind of the nice thing about it and why we use it. And it's industry standard. We can take our models from Keras and then port them over to Tensor or to any other architecture. So it's fine there. But once we use that, or once we've trained our models, then we can kind of feed in our technique and answer the real question, okay, given this output that we want, what's the input that will get me that? What's the meta-atom shape? So we've done the work on that already, and so these are some of the results that we get. It's very accurate, so basically read this as 96.5%. We can do this a million times faster. I think I'm hitting the time, so I'll go through these last slides quickly. The predictions are not perfect, of course. There are issues. Sometimes the shape is more or less right, but the other predictions of the output are wrong. Sometimes the shapes are wrong, but they actually get the output that you're actually interested in. So it's not flawless, but generally it's a fast and efficient way of doing this inverse design, or solving this inverse design, at least in electromagnetic problems. We've incorporated several different packages in our Mazy project. This is the shape prediction. So we basically use computer vision technology to kind of outline the shapes that we generate. And this is for our manufacturer. They can't take these bit maps. They need the polygons in order to kind of do the fabrication work. So that's why we had to incorporate it into Mazy as well. So, but we have that capability as well. So once we build that, Mazy's set up for optical design, but it's not limited to that. And I just kind of wanted to, that's why I scratched out the physics and then put relations. We have all kinds of applications, that spaces that Mazy is capable of working with. But optics is just one of them. And we're kind of ready to kind of apply it to other spheres of technology. So with that, I open the floor to the next talk, so to speak. Thank you for your time.